Hello, class! This chapter we will only describe motion in one dimension. Another word often used to describe motion is kinematics. The first concept you're going to learn is the difference between distance and displacement. Distance is the actual path traveled by an object as represented on the graph by a dashed line, and displacement is a measurement between the starting and end point. In this particular case, the actual path traveled is 70 meters, but the displacement is only 40 meters. Another way to think about the difference between distance and displacement is imagine that you're hiking through the woods on a windy path. The distance is represented by the actual trail you hiked on, and the displacement is a measurement between the start and the end point of the hike. Take note that you actually never traveled along the displacement. To understand the equation that represents displacement, we first must know that the variable x in this class will represent the position along the x-axis. The symbol delta is used in this course to represent the change in a variable. Another way to think about delta is that it means the finish point minus the starting point. So what do you think delta x means? Correct! Delta x stands for the change in position. The change in position is a definition of displacement. So that means displacement equals delta x. Mathematically, this can be written as the finished position represented as x of 2 minus the starting position represented as x of 1. Below is an example of a positive displacement. According to the equation x of 2 minus x of 1, the displacement equals 20 meters. The next example shows a woman running, or more like power walking, in the negative direction. This time, when you use the displacement equation, you would get negative 20 meters. An important concept to remember here is that the direction of the displacement is represented by either the positive or negative sign in front of your answer. A formal definition of speed is how far an object travels in a given time interval. What you need to understand is that the average speed equals the distance over time, which is represented by the variables below. The bar over s just indicates that the speed is an average. In this example below, we already learned that the distance traveled is 70 meters. Let's pretend that the graph represents a football player running a play. And let's say it takes the football player 10 seconds to travel 70 meters. How would you solve for the average speed of the football player? That's right. You divide 70 meters over 10 seconds. Thus, the average speed of the football player is 7 meters per second. The difference between speed and velocity is that velocity includes direction. So mathematically, the average velocity equals the displacement over time because displacement also depends on the direction, whereas distance does not. If we again pretend that the football player is running a total distance of 70 meters in 10 seconds, what would the average velocity be according to the graph below? Great job! You would take the final position of 40 meters and subtract the starting position of 0 meters and divide the whole equation by 10 seconds to obtain the average velocity of 4 meters per second. Now, please take note that the time is still 10 seconds for solving the average velocity, even though the football player took 10 seconds to actually travel the distance of 70 meters. Now take a moment to answer this question. Why would we use velocity instead of speed for experiments? We'll discuss your answer during our next class section. We won't use the definition of instantaneous velocity too much in this course, but I want you to at least understand the concept of instantaneous velocity, and that instantaneous velocity means that it's a velocity at a moment of time. For example, let's say a car travels at a constant velocity of 40 kilometers per hour. At 0.1 hour, the instantaneous velocity reads on the odometer is 40 kilometers per hour. At 0.3 hours, the instantaneous velocity is still 40 kilometers per hour. It would happen to be that this example has an instantaneous velocity and an average velocity both equaling 40 kilometers per hour. In the next example, the car is varying its velocity. At time 0.2 hour, the instantaneous velocity happens to equal the average velocity of 30 kilometers per hour. However, at 0.1 hour, the instantaneous velocity is instead 50 kilometers per hour, whereas the average velocity is still 30 kilometers per hour. At 0.4 hour, the instantaneous velocity is 20 kilometers per hour, and at 0.5 hour, the instantaneous velocity is 0 kilometers per hour, but the average velocity always remains 30 kilometers per hour. The next concept to understand is acceleration. The definition of acceleration is a change of velocity over the change of time. Mathematically, we can represent acceleration by delta v over delta t. Please note that the initial time for pretty much all problems we'll deal with in class will be 0. In the example, we have a car starting from rest and quickly accelerating to 75 kilometers per hour in 5 seconds. How would you solve for the acceleration of the car? Excellent start. By applying the equation, you get 15 kilometers per hour second. However, the units are a little funky. Can you change this answer to units of meters per second squared? To do so, we use unit conversion to change hours into seconds and kilometers to meters. To check and see if you set up the conversion correctly, all undesired units should cancel out. After plugging and chugging, you should get 250 meters per second squared. Now, the previous example showed a positive acceleration. Can you solve for this example below? Yes, you're correct again. By applying the equation, you should get a negative answer. Please be aware that there is a difference between negative acceleration and deceleration. Negative acceleration only depends on how you set up the coordinate system, and deceleration only occurs when the object is moving in the opposite direction of the acceleration, as shown in the picture below. Here you can see mathematically that the change of velocity is positive 10. Thus, the acceleration must point in the positive direction. Since the acceleration direction is opposite of the car's movement, that must mean that the car is decelerating. Lastly, I want to briefly touch on the instantaneous acceleration. Just like instantaneous velocity, instantaneous acceleration occurs only in a moment of time, as shown by the yellow stars below.